So the topic we're going to do is kinematics, and kinematics basically means objects in motion. So basically, before going over all of these examples, I would like you to go over this key. So it is much easier to remember what variable or alphabet was used to represent which quantity. So the lower cap D is to represent distance, the lower cap S is used to represent displacement, the capital S is used to represent speed, the lower cap V is used to represent velocity, and the lower cap A is used to represent acceleration. So we would go over the first equation of motion, and that is basically dependent on what is the definition of acceleration. Acceleration is basically rate of change of velocity. So if you frame it into a sort of an equation, it becomes acceleration equals to change in velocity divided by the time. So the change of any quantity is basically delta v in this case because it's velocity, or it also means final velocity minus initial velocity and divide by time. So this is represented by this specific formula, and where final velocity is represented by the variable v, the initial velocity is represented by the variable u, and the time is represented by the letter t. And what is done is just t is cross multiplied with a, so it becomes at times v minus u, and it is just rearranged the formula to make v the subject, and it becomes v equals to u plus at, or in wordings it becomes final velocity is equals to initial velocity plus acceleration times the time taken. So this is the first equation of motion. Moving on, the second equation of motion is based on the formula of distance, and that is distance is equal to speed into time. However, this specific formula is valid only when the speed is constant, and when the speed is not constant, this formula cannot be used. So there is another formula, but just an addition of a word average, and the remaining formula remains the same. So it is distance is equals to average speed into time taken, or displacement is equals to average velocity into the time taken. And we already know that average is basically the final velocity plus the initial velocity divided by 2. So basically this gives us the average into the time taken. So this gives us the formula, and we have just replaced it, these words, with the letters we just saw over there in the key, and displacement is replaced by the letter S. Average velocity, again final velocity plus initial velocity divided by 2 to take out the average, and into the time taken represented by the letter T. And this is our second equation of motion. Moving on to the third equation of motion, and basically we have to derive it. However, derivation is not required in the syllabus, but it is good to know how we derive any equation. So basically this equation S equals to displacement equals to initial velocity into the time plus half of acceleration into time squared is derived when we make v the subject from our equation number 1, that is v equals to u plus at, and substitute in the second equation. So v equals to u plus at, and in the second equation v is replaced by this u plus at, and the equation becomes u plus ad divided by 2 plus multiplied by t, and this equation and the brackets are open, and it becomes u plus at by divided by 2 into time, 2u plus at divided by 2 into time, and then it is just simplified. So the 2 and 2 get cancelled, it becomes 1 upon 2, and it is just simplified to ut plus 1 upon 2 at squared, or in wordings it becomes displacement equals to initial velocity into time plus 1 upon 2, or half of acceleration into time squared. And this is our third equation of motion. Moving on to the fourth equation of motion, and it is v squared is equals to u squared plus 2 into a into s, or in wordings it is final velocity squared is equals to initial velocity squared plus twice of acceleration into displacement. And again, this is an equation which is derived and derivation is not required. However, it is good to know. So again, make t the subject from equation 1 and substitute in equation number 2. So it becomes v equals to u plus a of a into t, where t becomes v minus u upon a, and it is just making t the subject. And what we do is just replace t in terms of v, u, and a in the second equation. So displacement is equals to average velocity into time. So the time is replaced by this specific expression v minus u upon a, and what we get is basically u plus v upon 2 multiplied by v minus u upon a. So v plus u, v minus u, when multiplied, follow this specific condition, which is v minus u, v plus a, and this is equals to v square minus u square, which is one of the identity in mathematics. So expanding it would give us v square minus u square upon 2a. So let me write it down. It would be v square minus u square upon a, and times 2 is equals to s. Just shift the 2a 2 cross multiplied with s, so it becomes v square minus u square equals to 2 into a into s. And making v square the subject, our formula becomes v square equals to u square plus 2 into a into s, and this gives us our fourth equation of motion. Alright, so there are some conditions in using these equations of motion, and that are: objects must be traveling in a straight line or moving in a straight line. Number 2, the acceleration of the object must be constant. And the reason is because if object is not moving in the straight line, then velocity would be changing, because velocity is our vector quantity. Okay, so now let's do two practice questions. So the first question says that the object starts at 40 meters per second. Then after traveling a distance of 60 meters, it has a speed of 20 meters per second. And then we have to find the unknown distance so that it travels and then comes to or comes to the position of rest and stop. So we could deduce that we have the distance, we know what is the final speed and the initial speed. So the best option amongst the formulas will be v square equals to u square plus 2 into a into s, where v square would be the final velocity squared, so 20 squared equals to 40 squared plus 2 into a into 60, that is displacement, and the acceleration would come out to be minus 10 meter per second squared. Okay, so now we have to find the displacement of this particular part of the motion. So as the condition stated that acceleration of the object must be constant basically throughout its motion. So what we could do is we could break this specific motion and like take this, treat it as a separate motion. However, this is a complete motion, but we could just treat it as a separate motion to just find out the specific displacement, and we know that acceleration would remain the same. So again, applying the same formula, v square equals to u square plus 2 into a into s, we know that the final velocity would be 0, initial velocity is given to be 20, plus 2 times acceleration is given to be minus 10, and displacement is unknown. And just rearranging the formula to make s the subject or displacement the subject, what would happen is minus 400 divided by minus 20 will give me my displacement, and the displacement comes out to be 20 meters. Alright, so we will move on to our next set of example, and it says that the object starts from rest, travels a distance of 40 meters, has a speed of 15 meters per second, then travels an unknown distance, and speed becomes 30 meters per second. So we have to find the specific displacement. So again, we know the break this specific part of the motion of object. We know the final velocity, the initial velocity, and the displacement. So again, v square equals to u square plus 2 into a into s. V square is 15 square equals to u square would be 0 square plus 2 into a times the displacement, rearrange the formula, and acceleration would come out to be 2.8 meters per second square. Then again, put the value of acceleration into this formula again, because same motion, so same acceleration, and find out the displacement by just putting in the values. We just calculated and we know. So making displacement the subject, the answer comes out to be 120.5 meters. So the trick is basically to judge which values are we provided with and to find the suitable or the best formula that could be used in that particular scenario. So next we have graphs of kinematics. So here is an example or a scenario where a ball starts its journey with a speed of 40 meters per second, goes up to the maximum position where it comes to rest, and then falls down again to a speed of 90 meters per second. And we are required to draw three types of graphs. One is the acceleration time graph, the other is the velocity time graph, and the last one is the displacement time graph. So we'll start off with the acceleration time graph, and assuming that upwards direction is taken as positive. So let's quickly make the axis. So here it is, positive acceleration, negative acceleration, and time. So we already know that there is a constant pull of gravity, and its acceleration due to gravity is minus 10 meter per second square. And since the gravity is acting downwards, that is basically in the negative direction. So we already know that the value of acceleration due to gravity 10 meter per second square would be minus 10 because it is in the negative direction. So what we will do is just simply make a straight line, because there would be a constant deceleration, and due to constant deceleration, which means a constant negative acceleration, so there will be a straight line graph or with a horizontal line in the acceleration time graph. Then moving on to the velocity time graph, and how would the velocity time graph would look like? Because acceleration time graph is a straight line, a horizontal line, so we already know what the velocity time graph would look like. And since acceleration is negative, so the velocity, and we already know that what is happening to velocity. Velocity starts from 40, goes to 0, and then increases to 90. However, this 90 is in the negative direction, so basically it goes up to minus 90 meters per second. So my graph would look something like this. So starts from plus 40 and would go to a maximum that is shown to minus 90 meters per second. So my graph would be a straight line, something similar to this. So this will be my velocity time graph, and then we move on to the displacement time graph. And we already know that the gradient of the displacement time graph gives us our velocity. So as we know that our velocity is decreasing, decreases from 40 to 0, and then increases again from 0 to 90. So basically to depict that specific part of motion of object, so what would happen is that the displacement time graph from 40 meters per second to 0 meters per second would look something like this. And you would all agree, because here the gradient is going from steeper, and then to a horizontal, which means the value of gradient would be 0, and hence it tells us that our velocity will also be 0. And then moving on further, from 0 meters per second to a speed of 90 meters per second, my gradient would increase, the gradient of displacement time graph will increase, and this will depict that my velocity of the object is increasing as my gradient is increasing. So this would be my displacement time graph of the object, and here would be my 0 meter per second velocity. since it would be at its maximum point in its motion. Then coming on to the second example, it says that an object starts from its rest position, falls down, bounces, and then goes back to its maximum position again. And it says the ball collides elastically with the ground and performs multiple bounces. Sketch the velocity time graph. And we already know what elastically bouncing means. It means no loss of energy as it bounces. And if there's no loss of energy, it means that over a period of time, the change in velocity would also be constant and it would travel through the same distance. So we already know what would happen, and since it starts from its rest position, and we again are assuming that our upwards direction is not positive, so going downwards, this would be my minus 50 velocity and this would be plus 50. So it goes from 0 to minus 50, and then from plus 50 it goes back to 0. So my graph would look something like this. So basically color matches the color, pink goes with pink and green goes with green. So my graph would go something like this. And then here a dotted line because there is a sudden change in direction because downwards, and then suddenly it goes upwards. So basically to depict this, we show the dotted line, then we go with this, and then it falls downwards again, and then again the dotted line to show the change in direction, and then when object fall goes back to its maximum position from the ground after bouncing from the ground. So this is some depiction of how my graph would look like. And one more thing, the time intervals, or I could also make time intervals like these or something like this. So the time intervals, and let me extend this too. So the time intervals would remain the same because 100% conservation of energy, so same velocity, and the distance traveled would also remain the same, and therefore the time would remain the same. And since 100% conservation of energy is there because it bounces elastically, so the distance traveled upwards, or the area of this triangle would be equal to the area of this triangle, would be equal to the area of this triangle and of this triangle. So basically the areas of these triangles would remain same, or equal would be equal because 100% conservation of energy. Alright, so moving on, if it says that the ball collides inelastically, so what would happen? And now we already know that if the ball collides inelastically, so over the course of every bounce, my energy would get lesser and lesser. So first it would go to its maximum displacement, or to at least comparatively to the maximum displacement, and then its displacement would slightly decrease, and then it would decrease further again, and then to show this change in direction, it would decrease again and again, and finally it would come back to 0 at one point in time. And we could already see that the distance traveled by the ball is different. Here it's the greatest, then here it's the second greatest, and then it keeps on decreasing and decreasing, and at one point it would be 0. So again, if it's inelastically, so there is a loss of energy upon impact, and we could already see that there is a difference in the distance that is traveled by the ball.